So last week I did a video about authenticating into AWS from Kubernetes, where I compared multiple approaches that could be taken depending on where the Kubernetes cluster is, whether you are using fully fledged EKS or not, and all other factors. So in that video I didn't go into too much detail because I promised that I'll do more detailed videos into each approach. So this would be the first video that I'll do, this time focusing on EKS Pod Identities. Now, if you watched my last video, you might remember that I recommended EKS Pod Identities only if you're using a fully fledged EKS cluster. This is because Pod Identities, the whole feature, is only available as part of the AWS API. There's a black box of functionality hidden behind an API operation that is managed by AWS itself. So while it might be useful for only certain situations, it is still worthwhile to go through the architecture and understand what's happening behind the scenes, because the more you understand about certain things, the easier it becomes to troubleshoot when things go wrong, or easier it is for you to design better solutions. So before I go into the architecture discussion, I'll first do a brief demo because it will be easier for me to map the concepts that I'll talk about in the architecture diagram to the demo that I just did. So I'm in my demo AWS account and I don't have a Kubernetes cluster yet, so I'm going to create one using EKS. So the first thing I need to do is to create a cluster, and I'll just go and create a cluster. Now, one thing I need to repeat here is that Pod Identities don't work with anything else other than an EC2 backed EKS cluster. So you can't just register an external EKS cluster through EKS connector and start using Pod Identities. I've tried to do that. I've tried to kind of trick the API, but it doesn't work if the EKS cluster associated with the work you're doing is not fully backed by EC2. So for this, I'm just going to go with custom configuration because I don't want to spend too much money on this. In this case, I'm going to create a recommended role for EKS to manage resources. So this will be an EKS cluster role, and the EKS cluster policy is automatically attached, and I'll just say EKS cluster role. The trust policy here for the role is set so that EKS is able to assume this role. Alright, so future me here. Now obviously all of the things that I'm doing here during the demo are not of production quality. I feel like I need to reiterate that. One of the strongest example of that is this trust policy that I have attached to this role. In all of my demos, I'm just going to use this simple trust policy where I just grant the permissions to a service principal. But in real life, there are things that you should be worried about, things that go bump in the dark, as they say. There are security concerns like confused deputy problem. So if you're doing this in production, just make sure to follow all the security practices and work with the permissions that are attached in that previous policy that we just saw. And I'm going to finish creating the role. Right, so if I go back here and refresh, I can see EKS cluster role. Just going to keep other settings the same. 1.31 is more than enough for my use case. That's it. So most of the settings here would be better for a production setup. I'm just going to go with a lean EKS cluster for the demo. So don't replicate these settings for a production setup. Just going to select the default VPC and strip it down to 2 availability zones. Just going to use the default security group. Keep it IPv4, and I'm going to switch to a public endpoint just for this case. But keep in mind, in production setups, keeping the endpoint private would be the best case scenario unless there is an excuse to make it public. So by default, keep the control plane private. If you have a really strong use case to make it public, consider it again and then make it public. I don't need any of these. I don't need logging. So here, this is an important step for Pod Identities. Now add-ons are basically different kinds of workloads, API server modifications, stuff like that. In our case, we can add the EKS Pod Identity agent here. Now I'll discuss more about the Pod Identity agent in the architecture discussion. Just keep in mind that if you're creating an EKS cluster from scratch, just ticking this box will do the trick. You don't have to do anything later. But if you have an EKS cluster that was created, let's say before this feature was introduced, then you might have to add this add-on manually. That can be done using either the AWS CLI or there's another CLI called EKS control. These are the same simple steps. You just go on and execute a bunch of commands that would add this agent into the EKS cluster. Right, I don't need a metric server. And I don't need anything else from here. Alright, so there's one detail I should emphasize on this step when it comes to the VPC CNI, which is basically the container networking provided by AWS. Basically, ENI is getting provision for different pod namespaces. In this case, just because we added the Pod Identity agent, we are going to have to map an AWS IAM role to a service account that is created for VPC CNI to work. Now, in this case, the service account is named AWS Node. So we are going to have to map an IAM role to that service account. The IAM role that is mapped to this service account should have proper permissions for the CNI plugin to start. So for that to happen, I'm going to create another role, and here I'm just going to double check that the use case is EKS Pod Identity. What that does is to make sure the correct trust policy is attached to the role that we are going to create. And here I'm going to attach the EKS CNI policy just to double check. There's a few different permissions attached to this policy, which makes it possible for the CNI plugin to start and initialize. I'm just going to keep the provided role name, just double checking that the trust policy is correct. It is correct because the principal here is pods.eks.amazon AWS. So basically a new type of principal that is used by Pod Identities feature. So that role is also created. I'm going to refresh this and it has automatically picked up the correct role. All the other add-ons are usually fine in most cases. So next, and time to create the cluster. This will take a couple of minutes. So I'm just waiting for the certificate authority details to appear here, because without that part of the control plane being provisioned, I can't really create the kubectl config for me to check the cluster status. So I'll wait another few minutes to see what the status is.
A few moments later.
Alright, so the EKS cluster is provisioned now. At least the control plane has been provisioned because I can see the certificate authority details there. I'm just going to generate a kubeconfig and start looking at the pods that are starting up, which are mostly to do with the add-ons that I added during the cluster creation. So for this, I'm going to create some temporary credentials and start working with the AWS CLI. Right, so the first command that I'm going to run is to generate the kubeconfig. So for this, the command we should use is update kubeconfig. So that adds a context to the kubectl config file and sets it as the active context. So if I just list the pods, I'll be talking to the EKS cluster. Right, I made a mistake. At this moment, we don't have any pods because we didn't add any compute capacity. I'm going to go back to the EKS web console and add an autoscaling group so that we'll have some nodes to play around with. So in this cluster, if we go to the compute tab, we have nodes and node groups. The best way to do this is to add a node group, which is basically an abstraction on top of autoscaling groups. And the node IAM role here is the IAM role or the instance profile that will be attached to the nodes. So I need to make sure proper permissions are attached to that role. So in this case, I'm going to create a new role for this. And this will be an instance profile. But there's a specific manage policy that I'm looking for that will have all the permissions needed for basic functionality of an EKS worker node. So I'll just do a comparison here. The minimal policy has just one permission, which is EKS auth assume role for pod identity. Now that is the minimum permission needed for pod identity agent to work, which is something that I'll discuss in the architecture discussion later. It might be better to just go for the full policy for worker nodes because there are a few other read operations that might be useful for certain agents, daemon sets, services that are running in the node to be successful. Also, just a note on this, because this is a detailed video, the container registry read-only policy provides permissions so that pods that are related with add-ons and everything else that are installed by EKS can pull from public container registries in AWS. So this is basically providing that permission. And CNI policy, like we mentioned before, provides permissions for the AWS VPC CNI to start successfully. So that one is created. I'm just going to go back and select that role. I don't need launch templates. I don't need any of the fancy details here. So for this, I'm just going to go for a spot instance, Amazon Linux 2023, which is kind of the latest Amazon Linux version available. And for this, I'm going to use T2 small because I want to keep my costs low. Just keep in mind that T2 micro might not work, especially because of all the add-ons that we added to the EKS cluster. Because remember, these add-ons run as pods inside each of these nodes. In most cases, there's a limit to the number of pods that can be spawned in these nodes. So T2 micro is a little bit too small for the number of add-ons we have in the EKS cluster. I'll just have one node. So this will take another 5 to 6 minutes because it needs to spawn up the EC2 instance. It needs to get the kubelet running. It needs the CNI pods to start and do all of that good stuff. So I'll come back when the node is ready.
5 minutes later.
So we can see that the EC2 instance has started, but the node is still in not ready state because the pods are still starting. The kubelet hasn't really successfully started. So we have a successful node at ready state. So we can start testing EKS pod identities. So as a DevOps engineer or as an architect, the first thing I should do is is to make sure that I have the correct permissions for the correct workload. That I can't really show in this kind of a demo because that really depends on the type of workload you're going to work on. But just keep in mind that you should always use least privilege principle. That means you should only give permissions for the workload that are absolutely needed. You shouldn't give umbrella policies. You shouldn't just give, for example, job role policies in AWS just because it is easy to do. So for this case, I have already created a role in IAM. This role is called EKS Pod Identity misc read, which gives the role the ability to read a specific object in a specific bucket. This is just a simple use case, but this could easily be a large policy that you have for a specific use case. So when creating this role, I made sure to attach the correct trust relationship. That means I should give the principal pods.eks.amazonaws.com the ability to assume role and tag sessions for this role. I'll explain in detail in the architecture section, but just make sure that you have this trust relationship established, otherwise pod identities will not work for this role. So now that I have the role set up, I need to go back to the Kubernetes cluster and create a service account to map to this role. In Kubernetes, we use service accounts to give permissions to workloads, pods basically. So we are going to create a service account and then map this role to that service account. I'll create a service account named pod identity test, and this is going to be on the default namespace. Right now we have the service account. Now we need to associate this service account with the role that I showed earlier. For that, I'm going to execute another AWS CLI command called create pod identity association. So the association is now created. I'm going to attach this service account to a pod definition and launch that pod. I'm going to make two modifications to this definition. I'm going to add a command so that the pod keeps running, and I'm going to attach the service account so that the pod will have the correct service account token when it is launched. Right, so just to iterate, the service account name here is the service account I created and mapped to an IAM role, and the command here just make sure that the pod keeps running for 1 hour at least so that I can execute into the pod and check all the details that I need to. So I'll create this pod now. Right, so the pod is in the running state. I'm going to describe the pod and check a few details. So the first thing I want to show here is these two environment variables, AWS Container Credentials full URI and AWS Container Authorization token file. Now, you might remember that I did not include any environment variables in the pod definition file itself. So these environment variables are being injected by something else. And in the mounts section, we can see there is a projected token volume that is attached to this pod definition, which we also didn't do in the definition file. So there is some mutation for this pod definition happening when we created that pod. So now I'll execute into the pod and see if I can download that specific file from the S3 bucket. Right, so the object has been downloaded, and we have the correct content. So I'll just try to do something else just to make sure I have assumed the correct role. So for an example, if I try to list buckets, I should get an access denied because I don't have that permission attached to my specific role. Right, so this is basically how EKS pod identities work. You can see that it is really easy to set up. You just create the IAM role, create a service account, map those together, and that's it. And then when you start launching pods, all the details that should be done under the hood are done for you by EKS. So like I mentioned in the last video, this is one of the reasons why AWS recommends to use EKS pod identities instead of earlier approaches like IAM roles for service accounts, because we don't have to do a lot of setup configuration before we start using EKS pod identities. You saw that when I created the EKS cluster, I just added the agent in the cluster configuration, and EKS made sure that the correct agent is installed and it is up and running. There are other components involved in this scenario. This architecture is actually complex compared to how easy it is to work with as an end user. So let me just go into an architecture diagram and explain what happened, because it's really interesting to see different components working together to simplify the end user experience. You can see that it is fairly complex compared to the simple diagram that I had earlier in the previous video. I found a lot of these details by going through the code for certain components and also by going through a few documentation pages and a few GitHub issues that mention certain undocumented scenarios. The setup here is that we have an EKS cluster inside of AWS which controls the API server in the background so we don't really see the compute resources that are being used by the Kubernetes API server in EKS. EKS manages that for us. We added a node using a node group, so all the compute workloads run on that node, and we made sure to attach the correct instance profile for those work nodes. So if I just retrace the steps that I did after creating the EKS cluster and attaching the compute nodes, what I did was to create a service account. So that service account was called Pod Identity Test, and after that I created an IAM role. Oh, I had already created that role. So if I go back to that role, this was the permission policy attached to it, and this was the trust relationship that I attached to that role. And then I associated that service account with the role that I created, and that was the create pod identity association command I executed in the terminal. And then I created a pod that got somehow modified by something running inside EKS, so that we actually had proper credentials when we executed the CLI command inside the pod. If I take a step back, creating the service account and creating the IAM role, I assume these are normal things that you do in day-to-day work when you work with Kubernetes and IAM. I'm not going to explain the details involved there, but I need to explain what happens when you add the pod identity add-on to an EKS cluster. The first component in this workflow is called EKS Pod Identity Webhook, which is a mutating webhook in Kubernetes that is added by EKS into the Kubernetes API server. So if you don't know, the mutating webhook in short is a component in the Kubernetes API server that is able to mutate pod definitions when a pod creation request is being scheduled. It can be used to do various things, but in this case what it does is to inject environment variables, the correct environment variables, based on how the credentials should be associated inside the running pod. The code for this webhook is open source, so you can check it out online in GitHub. Depending on whether a configuration file is provided for its runtime or not, the EKS Pod Identity Webhook injects different kinds of environment variables into a pod. Basically, there are two scenarios the webhook works with. One is called the STS credentials flow, which we will use in the next video when it comes to IAM roles for service accounts. But in this case, EKS has configured the webhook so that it uses the container credentials scenario. So in the container credentials scenario, it watches a file inside the API server that has a list of identities, basically service accounts and their namespaces that should be used to map IAM roles into a pod. So when I executed the create pod identity association command inside the terminal, what I'm assuming happened was EKS updating this specific file. So if any pod is created with that service account attached, the webhook knows that it should inject the container credentials environment variables into the pod definition. The other component in the pod identity scenario is called the pod identity agent. So pod identity agent is basically a daemon set that runs in every node that acts as a credentials server. So credentials server is basically a proxy server that can provide you credentials on behalf of you. So it can have any kind of logic that would provide proper credentials back to the caller. In this case, it runs as a pod inside each node as a daemon set. So when I ran the command to create a pod with that service account attached, what happened was it first got picked up by the mutating webhook, and it checked whether the service account is in the configuration file for it to inject the container credentials environment variables. So I had already created the association, so it should have been in the configuration file. The webhook decided it's going to inject two environment variables called container credentials full URI and container authorization token file. So if we go back to the pod and describe it, these environment variables were injected by that mutating webhook. Now the first environment variable of interest has this value which points to a link local address. Now I consider this to be undocumented behavior because although the documentation says that this environment variable can have a valid URI, every SDK actually does a check to see if this is on a link local address or on a loopback address. So the valid values here for this environment variable are either localhost, something that starts with 127, or anything that runs on link local addresses. For an example, if I go to the Java SDK, I can see that there's a check for the value to see if it is an allowed host, and what it basically does is to see if it is on a loopback address. And that is why the pod identity agent runs with host network property set to true, which basically says to use the host networking namespace as an init container. It can bind itself to this link local address and start serving any request that comes to it from any other pod. The second environment variable of interest points to a file which basically contains the token projected volume of the service account token. Now, if you're not familiar with this behavior, this is basically part of the relatively new feature called token request API in Kubernetes. Earlier, it used to be that when you attach a service account to a pod, there would be an opaque token that would get mounted to the pod. With token request API, you need to separately request a token for it to get projected into a pod as a volume. The token that is generated from the token request API can be what is called a self-contained token or a JWT. This JWT is signed. It can be authenticated to verify that it was issued by this specific Kubernetes control plane. So this becomes valuable when that token needs to be passed to other parties to be verified for certain operations. So now that the correct environment variables are injected with correct values inside the pod, when we executed AWS S3 API GET object, the SDK goes through what's called a credentials loading chain. The credentials loading chain is basically a list of providers that the SDK will look to get properly formatted credentials. I say properly formatted credentials because they don't really have to be valid credentials for the SDK to stop looking in this credentials chain. So for an example, you could have expired keys in your CLI configuration files and it would still count as proper credentials to be used, and the SDK will try to use that and fail because they have expired. One provider that has been added to this chain is called container credentials provider, and the container credentials provider works if these two environment variables are present in the runtime. When these two environment variables are present, it will make an HTTP GET request to the URI provided by the full URI environment variable, and it will pass the contents of the token file as part of the authorization HTTP header. Now, one detail here is that authorization header doesn't have any prefix like bearer or basic. It only has the token value as provided by the token file environment variable. In EKS Pod Identity, this credential server is the pod identity agent that I mentioned. The agent then makes a call to EKS to get credentials on behalf of the pod. The operation is called assume role for pod identity, and when making that request, it passes the service account token that was passed in as part of the credentials server request. So the details after that are not really visible because it's behind the EKS proprietary implementation, but it's not hard to guess that EKS will probably be verifying the JWT that is passed in this call using the OIDC details available from the Kubernetes server, then looking up the IAM role that was mapped to the service account, and then executing an assume role operation into that role and passing the details back to the identity agent. So identity agent just passes those details back to the caller, the client, and the client is able to make any AWS request as long as the permissions attached to this role allows it. One more detail here is that when making the call to EKS, the pod identity agent itself uses the instance metadata service provider in the credentials loading chain. It is actually the last part of the credentials loading chain. If this fails, the SDK will just fail to look up credentials. So in this case, two parts of the AWS SDK's credentials loading chain is being executed at two different places, which is kind of cool if you think about it. So just to cover all the bases, if we go and check the contents in the projected token volume, we can see that it is base 64 encoded. So you can see that this is a typical JWT which has the header and the payload base 64 encoded with the signature following it. So I'm just going to decode the payload and see what it contains. And we can see in the payload, we have a proper JWT with some claims that can be verified with the signature and the header attached to the complete JSON Web Token. And if I go to the worker node role that I created, the instance profile role, it basically contains the worker node policy that provides EKS auth assume role for pod identity permission. So like I mentioned in the diagram, the identity agent needs that permission for it to execute this action. And also that is exactly why this role should have a trust policy that lets that specific principal from EKS to assume that role. So if we go back to the role, we can see this is the specific role that I needed, and the trust relationship contains this principal so that it is able to assume the role. So that was basically the detailed architecture of pod identities inside of EKS. There are a few details that I'm not 100% sure about, mostly because I don't have access to the code that runs behind EKS, but we do have access to the code for the webhook and the identity agent, and with that and the documentation available, we can build a fairly reasonable model for what happens behind the scenes. Now, as I mentioned in the previous video, EKS Pod Identities can only be used with fully fledged EKS cluster. In one run, I actually tried to associate a service account with an IAM role by just associating an external Kubernetes cluster with EKS using EKS connector. It doesn't work because whatever that creates this association tries to verify if the EKS cluster is a fully fledged cluster or not. You actually get an error message saying that this type of EKS cluster is not supported for pod identities. And also a lot of this implementation depends on the fact that the SDK running inside the pod is up to date. So if you have legacy code that can't be updated, if you have code that you don't really have access to update the dependencies, then EKS Pod Identities is not a way to go. Mostly because these environment variables that are getting injected into the pod will not be recognized by the SDK. On the upside of things, you can see even though the architecture could be a little bit complex because there are a few moving parts that mutates the pod and serves credentials, what I had to do to get this up and running was really simple. I just spent a few minutes creating a service account and a role and then associating them together. I'll discuss what was there before Pod Identities was released by AWS. Now that was a lot more complex architecture with those complexities being exposed to the end user as well. So Pod Identities take that complexity away from the user. It presents a really simple interface, a really simple end user experience, and manages all that complexity behind the scenes. So I hope that was helpful for you to understand what's going on behind the scenes for Pod Identities. If you have any questions, don't hesitate to ask them in the comments. If this was helpful, don't forget to like the video, subscribe if you haven't. That said, that's it for me. Thank you so much for watching. I'll see you in the next video.